Well, good evening, everyone. A very warm welcome to the Astronomical Society of Edinburgh's November online meeting. I'm Neil Martin, President of the Society. And for those joining us on Zoom, please can you now ensure that your microphone is muted? Thank you. We have just the two items on our agenda this evening. In a moment, I'll formally introduce our guest speaker for this evening, Dr. Darryl Seligman. And following Darryl's talk and Q&A, I'll close the session with a look ahead to what we have coming up over the next few months. So let's begin. Darryl Seligman completed his undergraduate degrees in mathematics and physics at the University of Pennsylvania. He completed a PhD in astronomy at Yale University and was awarded the Yale University Dirk Brouwer Memorial Prize for Outstanding Ph.D. Thesis. After completing his PhD, he was a TC Chamberlin Fellow at the University of Chicago. He is currently a National Science Foundation Simonyi Scholar at Cornell University and Michigan State University. This NSF Astronomy and Astrophysics Postdoctoral Fellowship Award is made in recognition of significant contributions to the Rubin Observatory's legacy survey of space and time. And Darryl has just started as an assistant professor in the Department of Physics and Astronomy at Michigan State University. So, ladies and gentlemen, please welcome Dr. Darryl Seligman. Darryl, over to you.
Okay, thank you, Neil, for the introduction. And congratulations on becoming president of this renowned society. That's very exciting. Okay, so I have two preamble things I just thought of that I wanted to say to everybody written down. So let me try to make sure I can read my very bad handwriting. So the first thing I wanted to say was that, and I guess Nigel could not be here, but Nigel did tell me that basically the background level of expertise and understanding of astronomy I should assume is kind of like an undergraduate degree in physics or astronomy, but not, and that some of you are like ex-professional astronomers, so we have ex-faculty members in the room. Is it safe to assume that there's kind of like a baseline knowledge of physics and astronomy stuff, or I would love some input from all of the people who are actually here?
I think that's a safe assumption.
Safe assumption?
Yeah.
So terms like comet or outgassing even is okay?
Fine.
Yeah.
Fine. Okay, excellent. Yeah, I figured because you're all, I mean, I'm now understanding that you're all actually, some of you are even taking data on Thread Atlas, so I don't think it would be appropriate to tell you the very basics of comet physics. Okay. Nigel also said in his email to please, that you would all save your questions until the end. And that's typically how you go, kind of like 40 minutes of me speaking and then questions. Can I please ask that we don't do that? Because I cannot stand listening to myself for 40 minutes. So I don't want to subject all of you to listen to yourself. And more importantly, I am excited to kind of engage with all of you as a community and kind of learn about what you're doing here. So I was hoping we could have like a lengthier Q&A. If you just want to interrupt me during the talk and ask me questions, I would strongly prefer that. Is that cool, Neil? Or
That's super cool. Will, that's on you, my friend. Are you up for the challenge this Friday evening?
I am up for the challenge. If you want to interrupt me and ask me questions, tell me that I'm not speaking.
I'll make sure my glasses are on.
Okay, cool. And then the only thing I would ask is that if you're going to interrupt me, I'm totally cool with getting interrupted asking questions. But just because it's a virtual meeting, but I want to kind of interact with your community. If you ask me a question, if you're able to, if you could turn your video on, I would also appreciate that. Just because then I have at least a face and a name to put to that. I'm also just making sure I'm plugged into the Wi-Fi, into the internet. Can you hear me, or did you lose me for a second?
No, you're all good. You're all good.
Okay, great. So now I will start, but I'm hoping for some interruptions and questions. And if the question is, this is way too low level, we already know this stuff that you're telling us, that's also fine. All right. Let me get rid of this. Hang on one second. Okay, great. So everyone can see the full screen? Okay. So Neil, thank you for that introduction. It made me think. I think Nigel, I think you as a society are so on top of your schedule that you invited me well before I started as an assistant professor. So I was one of those NSF astronomy postdoc fellows when I sent the bio and the title, but I am finished that now. But as Neil kind of said, I just recently started as an assistant professor here at Michigan State University. And that, funny enough, timed up perfectly. I don't know if this was a good thing or a bad thing. Maybe in terms of my level of sleep, it was a bad thing, but probably like for excitement of science, it was a good thing that timed up perfectly with the discovery of 3I Atlas, our third interstellar object in the solar system. So that was discovered July 1st. I started as faculty August 15th. I know that I gave a talk at NASA headquarters about 3I Atlas my second day of class, and it was basically conflicting with my second class ever. So I had to tell NASA, like, I'm not missing my second day of class. So to talk about Atlas. So basically the timing of everything has just been totally crazy. So I appreciate all of you for coming and also for being flexible with me while we were scheduling this. First things first, is Andrew Farrow here? Oh, I see Andrew Farrow on my screen. Am I pronouncing your name right?
Hi, yes.
Hi, Andrew.
Hi.
Sorry to call you out. Are you okay with me calling you out?
Yeah, it's fine. No problem at all.
Okay. So basically, Nigel told me a few weeks ago that members of your society were actively taking observations of 3I Atlas. And then he sent me this as of like a couple days ago, which it is my understanding that, Andrew, you obtained this image of 3I Atlas.
Yeah, it's just on a C-star 50, as it says, on the 19th, so a couple of days ago. I thought, well, yeah, I got up about 5:30, and
Nice.
it proved worthwhile, even
Very
though
cool.
Starlink tried to muscle in on the act.
Okay, so Andrew, can I reserve the right to call on you a little bit later in the talk?
Anytime you like.
Update on this. Okay. So I'm super excited to talk to all of you because I think it's really, really important that, I mean, as you probably know, the second interstellar object was discovered by a quote unquote amateur astronomer, Borisov. But it turns out that amateur astronomers a lot of times give us significantly better data even than the professional astronomers are able to get. So I think I have a secret goal here that also I want to encourage all of you to keep taking data on 3I Atlas, because that can be super helpful for example, NASA or the Minor Planet Center for making the orbit or characterizing the light curves. So I wanted to show off this really amazing image that Andrew got a few nights ago, and I'll get back to kind of that. But so as I said, I'm Darryl Seligman, assistant professor of physics and astronomy at Michigan State, and I will tell you about the third interstellar object, 3I Atlas. I also am going to tell you, I don't want to just focus on Atlas. Atlas is going to be the main star of the show, but I also want to tell you about some background about Oumuamua and Borisov, the other interstellar objects. I'm going to talk a little bit about dark comets too, which are inherently related to the interstellar objects. And the goal of all of that background, on top of giving you kind of up-to-date information about 3I Atlas, is to explain to you the exciting things at the population level that we can learn about interstellar objects and what they tell us about planet formation and exoplanets throughout the galaxy. So to start, has anybody seen this video before? I always kind of interested for different kind of groups of people from different backgrounds, if anybody has seen this. I don't know if you can get like a raise hand or something like that. So probably, okay, perfect. So we got one chat. Am I able to check that, or can somebody just read me the chat? Is that easier?
Yeah, we've got a no, and I can say that I've seen something similar, not this particular video, but I've seen something similar.
Okay, so probably mostly no. So I did not make this, but basically this is all of the known as of a couple of years ago, all of the known exoplanetary systems throughout our galaxy. I know that we have people here who are very familiar with exoplanet systems, so I'm not going to go on too much about exoplanet science in this talk. But the point of this video, these are animations showing the diversity of exoplanetary systems that we know of throughout the galaxy. So the solar system is shown to scale, and on the back as the backdrop, where you have the terrestrial planets and then the giant planets further out. And then these are a bunch of different exoplanetary systems that we know of with 2 scale sizes of planets and orbits. What that is telling you really is it's not like I want you to just focus on a single one of these planetary systems. It's just to show you that what we have learned in the last 20, 30 years of exoplanetary science is that the physical processes that went into planet formation are ubiquitous throughout the galaxy. So what happened in the solar system, even though it's still it depends who you ask and how you look at it to say if the solar system itself is unique. There are aspects of the solar system that we don't see in exoplanetary systems, but one thing that we do know now for sure, even though we don't understand planet formation from ground up physics first principles, we do know that planet formation appears to be ubiquitous. And basically every star in the galaxy likes to form planets, has planets, and they come in a diversity of shapes, sizes, and orbits. Excuse me, sizes and orbits. While we don't totally know how planet formation unfolds, because we can't go back and watch that happen in the solar system, the composition of small bodies within the solar system have given us a lot of insights into that process, because these small bodies are literally the remnants of planet formation. I don't think I need to convince anybody here that comets and asteroids are interesting, given that we have members of your society who are literally taking astronomical observations of asteroids and comets, but just for some background context of what we can learn about them. They do tell us kind of some of the initial conditions of planet formation in the solar system. For example, we have all of these different types of small bodies in the solar system, and each category of small body basically brings a different piece of information to the puzzle of planet formation. We have things like near-Earth objects, which are shown here on the left. Near-Earth objects, because they don't have active dust tails, we typically think of them as inactive. And for the rest of this talk, I'm probably going to say active and inactive quite a lot. That means having a cometary dust tail. So these near-Earth objects have spent a lot of time close to the sun, presumably, or at least what we used to think, is that none of them have any ice left, and that's why you don't have a cometary tail. Then, when you go out past Neptune, you have an entire new reservoir of objects called in the trans-Neptunian population, or trans-Neptunian objects. These are bodies that are composed of both ice and rock, and we only discovered this outer reservoir of icy comets back in 1993. So we have a huge reservoir of small bodies out past Neptune. And finally, I mean, this is the definitions, as I'm going to tell you more about in the talk, get a little blurry, but classically, the last population is comets. And comets, what I'm showing you here, this is the European Space Agency Rosetta image of 67P, a comet that the spacecraft got close to and actually landed on. What you're seeing, can you see my cursor? Hopefully you are literally seeing this. Can you see the cursor? So what you're seeing here is the production of the tail of a comet. So basically there's ice in this object. It gets close to the sun for maybe not the first time, but it gets close to the sun for the first time in a while. Hasn't spent much time close to the sun before. That ice, that fresh ice, kind of heats up and it sublimates, which means it turns from an ice into a gas and blows off. And what you're seeing are little dust particles that come along for the ride with the ice and reflect sunlight. So our classical kind of understanding of comets is that they are leftovers of planet formation. They tell us about the building blocks of planets. And by looking at things like if they're active or inactive, that can tell you about their composition. However, there is another, this isn't an alternative reason, but another complementary reason why scientists and amateur astronomers like to study small bodies like comets and asteroids. And that is that they are able to transport material throughout the solar system. So small bodies are one of our best mechanisms to transport material throughout the solar system, and most specifically from the outer reservoirs like the Kuiper Belt into the inner solar system where the terrestrial planets are. The reason that is so important is because that is a possible mechanism by which we can transport material like ices and organic material from the outer solar system to the inner terrestrial planets. And that can be vital for the development of life. So one reason to study comets, for example, is that what I'm showing you here, this is this plot on the y-axis is the deuterium to hydrogen ratio in water. If you just kind of forget the specifics of what that is just a marker of the chemical composition, okay? So the point of this is that the Earth, the origins of the oceans here on Earth are still an open question in geoscience and planetary science. We don't actually know where the Earth got its water from. If you look at something like the deuterium to hydrogen ratio as an example, the Earth's oceans, the water doesn't match up with what we see in the interstellar medium and in the protosolar gas, from which the the solar system formed close to the Earth. So what that's telling us is that one possibility, and this is something that this is one of the leading hypotheses, but we're not sure, is that the Earth formed without its water and the oceans were delivered by things like comets and asteroids, which had ice on them. So that's one of the main reasons why we study comets, is they potentially delivered water and other things to the Earth, which were essential prerequisites for the development of life. Any questions at this point? Okay, I think I saw a chat question, but okay, I'm going to keep going. So another more specific thing about small bodies is that when we look at the chemical composition of a comet specifically, the differences in compositions can roughly be traced to where that small body formed. Just a real quick question. Do you see the set of Zoom cameras, like all of your faces? Do you see that, or is it just me seeing that?
We see your screen plus a gallery of images across the top.
Okay, I'm going to try to move okay. So you can't see the whole slide. Is that correct?
Yeah, we can see the whole slide. Yeah.
Oh, okay. It's only me who cannot see the whole slide. Yeah. Okay, so it's just me who cannot see this. I think I could go on without seeing the whole slide, but as long as you can see the whole slide. So basically, the differences in compositions of small bodies are going to trace where that small body formed. If you take, for example, this is the solar system, but it also can apply to exoplanetary systems. We know that these systems form in protoplanetary disks, which are, after the star forms, a disk of gas and dust which forms around the star. In that disk, you form comets, asteroids, and then eventually planets. The further out you are in the disk, the temperature decreases. And so astronomers like to talk about these things called snow lines, which is basically saying when you're out far enough for something to freeze out, for example, water to freeze out, then all of the water that's in the disk, in the gas, will freeze out onto the dust grains, which are going to form the comet in the first place. Now, basically, the fundamental idea here is, in the solar system, as a very approximate, the water snow line is about where Jupiter is, and then the carbon monoxide snow line is out past Neptune. So really what that's telling you is that if comets form exterior to a snow line, then they should have that ice incorporated in them. So when you go and make measurements of a comet, if you see that ice in their outgassed material, then you can infer something about where they formed in their host disk. So for example, if a comet forms somewhere between Jupiter and Neptune, then it should be enriched with water ice, but it should not have carbon monoxide ice in it. And alternatively, if you have something that forms way further out, let's say all the way out past Neptune, then that object should have both water and carbon monoxide incorporated into it. So when it gets close to the sun and we take measurements, then we'll be able to see both water and carbon monoxide being active. So that is a more specific reason to take observations of comets, is because from measuring the composition of a comet, you can say something about the environment in which it formed, and specifically the formation location within a host disk, which is critical for our understanding of planet formation. Up until recently, our insights into the compositions of small bodies outside of the solar system was entirely limited to observations like this. So while we've had lots of observations of small bodies in the solar system, we didn't have the opportunity to look at small bodies like comets and asteroids that formed in these exoplanetary systems. All we were able to do was look at the agglomeration of all of those objects as they orbit other stars. So this is an example of a JWST image of a debris disk. So this is something like a Kuiper belt, but around another star. This is this is an unprecedented, amazing window into exoplanet science, because you're looking at things that formed into planets or potentially can form into planets, or the leftovers of planets in an exoplanetary system, but you only get to look at the whole population. You don't get to look up close at any of them until now. So that's the big lead up until now, because we have these interstellar objects moving through the solar system. The interstellar objects were first discovered in 2017. They're the three we know of: Oumuamua at the top here, Borisov, 2I Borisov, that's the second one on the right. And then the bottom is 3I Atlas, the star of the show, because we are literally observing it like right now. And Andrew got an image of it a couple of nights ago. These are objects small bodies that formed outside of our solar system. And we know that because they have hyperbolic trajectories, which means they're unbound from the solar system. They come, they leave, they never come back. And that's how we know that they formed outside of the solar system, as opposed to the comets and asteroids that we have native in the solar system, which keep orbiting round and round. These are other planetary building blocks, which are getting delivered straight to our doorstep, and that we now have as a complementary line of research evidence into planet formation in exoplanetary systems. We have this unprecedented view, up close view of planetesimals from other systems. And I'm really excited to talk to all of you, because as I kind of said at the beginning, this 2I Borisov, this is named after an amateur, quote unquote, amateur astronomer. That all that means is that it was not a survey that, a survey that got the images, but Borisov has discovered many comets. So a lot of times the amateur astronomers beat the surveys to finding things. So I think it is extremely important. I think most of you probably already know this, but it is extremely important that amateur astronomers who have other jobs as well, who do other things, but are extremely good at taking astronomical observations, share that information with the scientists, so that together, as a truly worldwide community of astronomers, we can characterize these once in a lifetime opportunities to study planetary building blocks. Okay, any questions there? Okay. One thing you might have as a question is that if these interstellar objects are really ejected from their exoplanetary systems, can they really teach us about the compositions of other planets? So my answer to that, this is kind of more motivation for studying the interstellar objects, but I want to convince you that by studying 3I Atlas and interstellar comets, we really do get a window into exoplanets. Not just the remnants, but we really are going to get a window into understanding potentially habitable planets around other stars. Let's go back to this idea, this kind of picture that I painted earlier. We have now an exoplanetary system, not the solar system. In that exoplanetary system, this is just my cartoon exoplanetary system, okay? But this can be representative of many different types of exoplanet systems. You have a giant planet, and then you have closer in, you have a rocky planet, like, let's say it's a habitable, quote unquote, habitable rocky Earth-like planet. We're going to start with the idea that we have a bunch of comets that form at a really high distance in this system, okay? So these comets are going to form really far out, outside the CO snow line, and they're enriched in material like water and carbon monoxide, material that can be critical for the development of life on a planet. The existence of the interstellar objects to date have told us, just the fact that we discovered these three so far tells us a lot more should be out there, not only in the solar system, but throughout the galaxy. In fact, they tell us that the galaxy should be filled with about enough such that every exoplanetary system ejects about an Earth mass worth of material of Oumuamua Atlas-like interstellar comets into that galactic population. So if that happens, one way that that can happen is that that giant planet in your exoplanetary system gets close to one of these comets and ejects them. But basically, that ejection process is chaotic. What that means is that a lot of the time, those material will get injected into a solar system, into an exoplanetary system, as opposed to being ejected. And if that were to happen, all of a similar amount of material should be injected from the outermost regions in exoplanetary systems to places where you have rocky, potentially habitable exoplanets. What that means is that of currently known exoplanets, these interstellar comets that we're observing should have every exoplanetary system should have an analogous population of small bodies just like that, look exactly like the interstellar comets, because they came from the same reservoir, that were actually transported to the innermost regions of those systems. And what happens is that if those comets get close to these rocky planets, they can get accreted onto them. That means, just like, I think a lot of you probably know about or even remember the Shoemaker-Levy 9 event, when there was a comet that was basically disrupted and accreted onto Jupiter. That could happen easily in these exoplanetary systems. And so what that really tells you is that when you look at an interstellar comet, you are looking at the material of something that is representative of material that could have been delivered to a potentially habitable rocky exoplanet. So just like in the solar system, how I started this by telling you that the comets in the solar system, it's possible that the ones that start all the way out at the Kuiper Belt were transported to the inner regions of our solar system and potentially delivered water to the Earth. Something very similar could be happening in exoplanetary systems, and these interstellar comets are a window into that. So these interstellar comet analogs could potentially be bringing material which is critical for the development of life to potentially habitable exoplanets. So I started this with—
Hey, Darryl, can I ask a question here?
Absolutely. Thanks, Mike.
It's Mike. Yeah, I'm just kind of thinking about what you've said there about Jupiter's kicking comets out and sending them into the solar system. And that's got to be because of velocity perturbations caused by the gas giant. Now, in order to get a comet to Earth, you've got to have a range of velocities that won't be the full range of what kicks it in. Do you have any feeling for what fraction of that one Earth mass of comets could potentially be hit Earth or be attracted to Earth out of that velocity distribution?
That is an excellent question. Okay, Mike, so you clearly know a lot of physics. I think I'm gonna not go through I will not go through all of the details of how the physics work. I could answer that maybe after, but sure. Essentially you get the first answer to the question is yes, I have that exact number shown here. So it's kind of like a backup slide. So I will just show it and explain it. The thing that saves you, Mike, that is a very apt question. The thing that saves you is that the orbits keep changing. So it's not just one. So the idea is that in an exoplanetary, this happens in the solar system, right? Jupiter sends stuff in, but in an exoplanetary system, you will, if you send a bunch of material to the rocky planet regions, they will just sit there and keep orbiting until they interact with a planet. That's what saves you from your, but you are totally right about your question. But the short answer to that, what fraction of them are going to get accreted, that actually, the main thing that drives that, okay, so there's two parts. One is that knowing that Oumuamua was discovered tells us that on average, every star ejects about an Earth mass of material. That is a lot of comets. That's like 10 to the 12 comets, actually. So there's a ton of this stuff getting kind of like going into the inner regions and bombarding these planets. But then the planet themselves, depending on how, it's like, depending on how big the planet is, that tells you, and how far from its star, that tells you how good it is at accreting. So the closer in you are and the more massive you are, then the better you are at accreting these comets. So this plot here, this is a backup slide, but you asked, perfect. I have the answer right here.
Good.
So the x-axis is semi-major axis. That's like distance from the star.
Yeah.
The y-axis is mass. Each one of these points is one of our currently known exoplanets. Okay, so you probably have seen these kind of talks about exoplanets. I can't see my cursor, but basically the bottom left quadrant are the rocky planets. Those are the ones that we're potentially interested in getting water delivered. The color that I have here, that's the difference. The color is the fraction of those comets that interact with them will get accreted. And so basically, I won't tell you how I calculated it. It's just a few like physics lines, basically. But the yellow points are things that the minute they interact with a comet, they're going to accrete that because they have really strong gravity and they're close to their star. So basically, the short period rocky planets are amazing at accreting comets. Jupiter is actually very bad at accreting comets. That's why it's always sending stuff around. The Shoemaker-Levy event is kind of an outlier. So the exoplanets that we know of, those short period ones, are the ones there you could really see evidence of comet enrichment from things like interstellar comets. Does that answer your question?
It does. Maybe at the end I'll ask you, sir, another question about it, which would be, that's fine. It looks great for a single planet, but obviously if you've got 3 or 4 rocky planets, they're going to be dividing this stuff amongst them.
That's true. That is true.
Okay, cool.
Yeah, we'll talk about that after. But yes, also in the solar system, same thing, right? So that's an excellent question.
Thanks.
So the answer is, if these interstellar objects, this is all motivation for studying interstellar comets, but yes, they are of, they really can tell you about the composition of these exoplanets. And I think really what's exciting moving forward is linking the observations we take of interstellar comets to observations we take of exoplanet atmospheres and seeing if you can draw some large scale connections there. So my plan was to give you motivation for why to study comets and interstellar objects. Next, to tell you about the 3 interstellar objects we know about with a focus on Atlas, which everybody wants to know about. And then I was going to tell you about dark comets next, which is this new population that are kind of related to Oumuamua that we've discovered in the solar system, and then end on future prospects. If I don't have time for all of that, because I do have a timer going, I would much rather hear your questions than blabber on at you. So if I have to cut section 3 about dark comets, that's fine. So I can basically keep, I am like in my head, I am on track. The first interstellar object, 1I Oumuamua, was discovered in 2017. Can you still hear me all right? Or did I, the mic still good?
All good, all good.
All good, awesome. So this is an image that Dave Jewett took of Oumuamua with the Nordic Optical Telescope. And this object was phenomenally interesting and mysterious for many different reasons. I'm not going to spend a lot of time talking about Oumuamua because it's kind of old news and everyone wants to hear about Atlas. But Oumuamua basically defied all of our expectations for what an interstellar comet should look like. The main reason was that it didn't look like a comet. So as you can see here in this image, it is just a point source. So it doesn't have an extended tail. Like I am seeing on my screen right now, Peter Black. You have your background image is just of a comet. Oumuamua it's perfect for me because I could like compare them. I should have put an image like that right here, I guess, in comparison. But basically a comet tail that you're used to seeing, like Andrew's image of Three-Eye Atlas, you didn't see any of that with Oumuamua. So it's presumably it didn't have any ice. It wasn't outgassing at all. However, it basically defied every rule of being a comet as defined by our solar system standards. The main reason is that it didn't have that cometary tail, but it did have a comet-like non-gravitational acceleration. A non-gravitational acceleration, just in case you don't know, I know we have comet experts in the room, so most of you probably know, but when comets outgas, when they get close to the sun, that outgassing material, basically ice turns into gas, and then that produces a rocket-like recoil. So that will produce a non-gravitational acceleration. So Oumuamua accelerated like a comet, but had no dust tail visible. That was very mysterious. And basically, without going through the details of this, I will happily answer questions about Oumuamua after, but we had to invoke new origins for what was driving the acceleration of Oumuamua compared to what we've seen in the solar system comets, just to try to understand how this object could have formed and what it could be telling us about. So I have this theory that well, Jenny Bergner really is the one who developed this. So Jenny Bergner developed this theory. She's a professor at Berkeley. We published this a couple of years ago, but basically the idea is that Oumuamua is a water-rich comet, but as it went through the reason it had that non-gravitational acceleration, no dust coma, is because it was severely processed by cosmic rays as it traveled in the interstellar medium, these very high energy particles that you're exposed to for hundreds of millions of years while traveling through the interstellar medium. Happy to answer questions about Oumuamua further, but I just want to keep the story rolling to get the Three-Eye Atlas in the interest of time. That was 2017. I was a third-year grad student at the time at Yale. 2 years later, I'm a fifth-year grad student. We get the next interstellar comet discovered by an amateur astronomer in Europe, 2I Borisov. It's named after him, but it is a little confusing because Borisov is really good at finding comets. So there's actually a ton of things named after this guy. So he found the second interstellar comet discovered in 2019. And a great thing about Borisov, the comet, not the person, is that it was unlike Oumuamua. It was definitely a comet. So it displayed a beautiful active cometary tail. The thing that I want you to remember about 2I Borisov is that although people kind of you'll hear people saying that Borisov was like, oh, Oumuamua was interesting. Borisov behaved just like a solar system comet. Its composition was very different from the compositions of solar system comets. So that is interesting, especially in the context of Atlas, which I'm going to get to in a second. What I'm showing you here, basically in blue is observations that we took of water, and black is observations of carbon monoxide. The x-axis is how far it was from the sun, or the time relative to when it was closest to the sun. The point is that where you had observations where there were sensitive to carbon monoxide and water, Borisov had significantly more carbon monoxide in it than water. And that is totally different from what we see in solar system comets. So that, even if you hear people tell you that Borisov was kind of a boring old solar system comet, just like that, it was not. And I'm going to try to tie that composition together with what we know about Atlas and make some inferences about what these interstellar comets could be telling us. So then there's 6 years and we don't find anything. And we're kind of, I even stopped working on interstellar. I was like totally obsessed with interstellar objects, 2019, 2020, 2021. I started working on other topics because we weren't finding any more. And then right a couple of weeks before I start my faculty position at Michigan State, bam, we get our third interstellar comet. So this is 3I Atlas. This is a phenomenal discovery and a phenomenal opportunity, and also a phenomenal apparition, which I'm going to explain in a few minutes. So basically, this object was discovered July 1st by Larry Deneau, who is part of the Atlas survey. That's one of the surveys, that all sky surveys looking in. He is based in Hawaii. They're based all over the world, actually. There's several telescopes, but the one that he was at was in Hawaii. Him and John Tonry basically found this object. And these are the actual images that they found 3I Atlas in. So Larry was looking, I think July 1st or the day before July 1st was doing kind of routine maintenance things up at the telescope and then spotted this object moving. These are basically an hour apart, 5:15 and 6:20. These are, and you can see in red, this is the moving object in the Atlas field. As soon as we confirmed it was interstellar, it was just, I mean, basically we found it, it was moving super fast. And then these, so Larry, so this page, okay, I can't get my cursor, but I want to do this. I want to point at the screen, bottom left of the screen, this paper that we published about the discovery of it. The second author is Marco Micheli. Davide Farnocchio is the third author, and then Larry is the fourth author. Marco and Davide basically are the European Space Agency and NASA JPL people who map the orbits of small bodies throughout the solar system for many reasons, part of them being planetary defense. Within like 12 hours, Marco and Davide were like, for sure. I was like, is this interstellar? They were like expecting a no, because, you know, the way this actually goes is a lot of times you'll discover something that has an almost hyperbolic orbit. We're like, oh, is that an interstellar object? And then I asked Davide and Marco or something, and it's like, no, it's not interstellar. This is actually just a long period comet. But within a couple hours, they were like, this is for sure interstellar, because the object was moving so fast, it had an eccentricity of 6. On the right here, this is the kind of top-down view of the orbit. So X and Y is looking down from the solar system. You see in blue the Earth's orbit, and then I'm actually colorblind. This was stupid of me. I think Jupiter's in green, but I'm not totally sure. But Jupiter's the one further out. So Jupiter is further out. And then we have the orbits of Oumuamua, Borisov for comparison, but then also of 3I Atlas. So this eccentricity greater than 1 is hyperbolic or interstellar. Atlas is an eccentricity of 6. So this thing was zooming through the solar system. Very exciting. We basically didn't sleep for like 7 days. So like we went from July 1st, discovery of this object. I didn't discover the object. Larry discovered it. Davide and Marco, and then a bunch of people that basically work with Davide and Marco's teams made for sure, figured out it was interstellar. And then it was just, I mean, within the first couple of hours, me and Marco were on the phone just trying to get any telescope to look at it. Like it was 1 a.m. for me and 7 a.m. for him in Rome. He was like, trying to get to his office, gets stuck in a traffic jam, like turns around. He's like, I'm coming back. It's not even worth it. We were just like frantically trying to get any observations to figure out. And within 7 days, we kind of got some initial characterization observations and submitted the paper kind of outlining what we knew about the object at that point in time. This was us like, I don't even know what we were like. I think Maxime here was showing us like the first color measurement we got on 3I Atlas at the time. Not totally sure, because I also was probably like extremely sleep deprived at that point in time. It's also probably why I had a really long, disgusting beard at the time, because I wasn't really sleeping or taking care of myself. But we were kind of all totally focused on characterizing this object. So I'll highlight some of the results that we got on 3I Atlas. Right near discovery was July 1st. These images that we got, I think we submitted this paper like maybe like July 8th. So we got these within 1 to 4 days, because these are actually stacks of images, what I'm showing you. But these were some of the first observations that we got of 3I Atlas. On the left is a stack of CFHT, that's the Canadian France Hawaii telescope. On the right, panel B, that's our VLT image. The reason it spans over a couple of different times is because we got a bunch of images with both telescopes, and then we stacked them all together. I'm sure there are some people here in the room who have done that with their own images. But basically the reason for doing that is to get better sensitivity of your data. And I kept, basically in the left, we kept the background stars. On the right, we subtracted them, but just so you know the difference, that's why we're showing it. We keep the background stars just to show how fast it's moving. So it's like we stack this object, it's moving through the sky. And so the background stars are showing you that it's moving fast compared to those background stars. They are there in the VLT image, we just removed them. And then what you can see, basically, if you look at the center, that's Atlas in the center, it's more apparent on the right, on the image from the VLT. But do you see that kind of haze to the right of 3I Atlas in the direction of west? That is clear evidence of cometary activity. The reason I say it's clear is because this object, when we discovered it, it was at 5 AU. So it was almost at Jupiter. And for a distant solar system comet, that is like exquisite evidence of cometary activity. So we knew immediately that 3I Atlas was an active comet. Any questions? I am totally happy with just taking out the dark comet stuff. So I'm just going to focus on Atlas, get to future prospects, and then take your questions. But please interrupt me if you have questions. I don't have Jim.
Hi, Darryl. From your previous slides, it looks like 3I Atlas is close to the planet solar system. Is it possible it could have picked up some matter from the Oort cloud, and that would change its characterization a wee bit in terms of what outgasses, or is that just going to be insignificant?
No, that's an excellent question. I guess so. Okay, the short answer to your question, that is a very good question. The short answer is that we don't know. But I will take you one step further. One thing that's possible is this thing was also moving through the galaxy for a long time before it got to the Oort cloud and solar system. So it also is possible that it picked up material in the interstellar medium. The only reason that we think that that is not the most efficient mechanism for material to be kind of like accrete onto it. Also, you have to remember that it is possible that as it travels through the interstellar medium, it also loses material, because there are for sure high energy photons and cosmic rays that hit it, maybe making some stuff outgas. So I would say it is entirely possible that happens, but it's also that what you asked happens. It's also entirely possible that it lost material, or it accreted material and then subsequently lost that. So we don't really know. One thing for sure, which is really interesting though, is that it is entirely possible that as it traveled through the interstellar medium and the Oort cloud, that the ice that you were seeing, that the ice that we're measuring was processed. So maybe from some mechanisms like what you're talking about, or cosmic rays or something, they came and hit. It's kind of like what we think happened to Oumuamua, but maybe changed the composition of the ice. So I think, okay, one way to be pessimistic is to say we have no idea what happened. My optimistic view is that these interstellar comets not only give us an unprecedented window into exoplanets, they also give us an unprecedented view into the processing of ice in the interstellar medium, which is very important for lots of different areas of astrophysics. Does that answer your question?
Yes, thanks very much.
Awesome. Great question, though. So what this is showing is, okay, this is basically on the x-axis is date. So this was where we were at when we submitted the paper. The x-axis is date, so it's like July 2nd, 3rd, 4th, 5th. And then the y-axis is the magnitude. So this was our there are like 50 authors on this paper, because basically like everybody was sending data. Like we were all just being very collaborative. I was trying to be as open and collaborative as possible. So we had people from all over the world sending data, trying to contribute, trying to figure out what was going on with this object so we can best characterize it, because it was such a great opportunity. The magnitude, that is basically how bright it is. The takeaway from this is that the object didn't change in magnitude very much. So we discovered it. It was for sure active out when it was past 5 AU around Jupiter. And over time, as we were observing it, it didn't change its activity level. Everyone loves this. So this is animations, some of the data that we were showing basically. My graduate student, Tessa Franke, shown here. She's a first-year PhD student here at Michigan State. She basically got observations for all of those nights, including July 2nd, but we used the SOAR telescope. These are two animations of 3I Atlas of the data. So this is basically, as you play it, you could see Atlas moving across the sky. You could see just how difficult it is to do these observations also, because like all of this background stars and stuff like that are messing with what we say is how bright 3I Atlas is. So I'll play it one last time, but you can see on the left, it's kind of a less crowded field, but on the right, that was a very difficult night. From all of that, we tried to basically get a composite light curve telling you how the brightness of the object changed over time. And what we can conclude was that near discovery, the object was kind of staying at the same level of activity. That's telling us that it was actively sublimating something. So some ice was driving the cometary activity, and that was kind of vigorously ongoing throughout the initial perihelion. This is nuts. So, has anybody heard of like a pre-covery observation? Do you know what that is? Do I have to define that? Okay, I think I'm saying, I'll just
finding that.
Yeah, so basically, a lot of times when we discover some cool new object, it turns out that it was sitting in another survey, maybe observable, that we didn't find it in for like a couple days before. So the Rubin Observatory LSST, which I'll talk about in a few minutes, came online and it wasn't fully online, but it was basically doing engineering nights before Atlas was discovered. And so we then found 3I Atlas in Rubin all the way back to June 21st. So almost 2 weeks before the discovery, we were able to get 3I Atlas in Rubin. And that showed us that I'm kind of building up a timeline of the observations at the top left here. That showed us that the object was also vigorously outgassing even back in June 21st. The craziest thing, though, is that we found 3I Atlas in TESS back to May 7th. Okay, so like TESS, if people don't know what TESS, I'm sure some of you know what TESS is. TESS is the NASA's Transiting Exoplanet Survey satellite. So this is a amazing satellite doing exoplanetary science, basically looking at not the whole sky, but a lot of the sky, and staring repeatedly at stars to try to find transiting exoplanets. But kind of fortuitously, 3I Atlas was in the field of TESS all the way back through May, but we found it sitting in the TESS data back to May 7th. And that's when it was past 6 AU. And one astronomical unit, when I'm saying AU, that's the distance between the sun and the earth. So we found 3I Atlas in TESS all the way out at 6 AU. So that is telling you potentially that whatever is driving the activity that we saw right when it was discovered, it must have been something way more volatile than water. Something like carbon dioxide, carbon monoxide. And then basically, I'm going to skip ahead just in the interest of time because I want to have plenty of time to answer your questions. JWST, Martin Cordner, I wasn't involved in this, but Martin Cordner got these amazing observations of JWST of 3I Atlas. These were taken on August 6th, and these confirmed that CO2 was driving the activity. So the top left and the top right is really the one that shows the CO2 activity. You've probably all seen this image because it's been all over the news for several months. This is what really is what's telling us what's going on. I'm sure some of you are used to looking at cometary spectra. The x-axis, for those of you who don't look at spectra every day, the x-axis is wavelength. The y-axis is flux. But you'll basically see features that are due to different molecules driving the comet. And the key thing is you see this huge peak around 4 to 5. That is from CO2. So that's how we know that 3I Atlas, basically from the TESS observations, because it was active so far out, we were able to say that it must have been something more volatile than water driving the activity. And then JWST confirmed that, which was amazing because we got this amazing detection of CO2. And here I just wanted to highlight again, I think we could do this more at the Q&A, that we've got people in your group who are actively taking observations of 3I Atlas. So I really encourage people, Andrew and anyone else who's getting data on 3I Atlas, to keep taking data and share it with, if you can submit it to MPC, even better, because that is very helpful for people who are trying to characterize the orbit, point at it for future observations, or even just figuring out what the level of brightness is through time. Okay, so that's where we were at before perihelion. And I know that we could talk about it at the Q&A. I know there was a press release with a bunch of NASA stuff that was released in observations of Atlas just 2 days ago. I am not a mission PI, so I don't want to speak for any of the PIs of any of those missions and like present their exquisite data. But basically, at this point, I want to say, given that we know that 3I Atlas's activity was driven by, at least when it was further out, driven by carbon dioxide, what can that tell us about planets and exoplanets? And then I will wrap up and we can go to Q&A. Does that sound good? Is that the timing good? Do people have a little time to say and ask their questions?
Yeah, the timing's great. There's plenty of time. Yeah,
Okay. So if I talk for like 10 more minutes, is that good? And then we have
it's
questions?
cool. Yeah, it's cool.
Okay. So if you remember, go back to that picture that I painted earlier. Excuse me, let me just. Oh, right. And I want to, we are at the point of this is that to be continued, like we are going to have more observations coming in and we have observations from people like you. All of that is super useful. And at this point, basically, I want to draw some population inferences, try to draw population inferences about what we can say about planet formation from these interstellar comets and the population of them, even though it's just a population of 3. So the caveat is everything I'm going to say about exoplanet formation is probably just from a population of 3, kind of really just from a population of 2, but we'll see if we find more of those objects, how that holds up. So here, remember I had showed you that the composition of a comet tells you about where it formed. And that's really by saying how much of things like carbon-based species like carbon dioxide and carbon monoxide is there compared to water. So one way to kind of visualize that is on the y-axis of this diagram, I'm showing the carbon to oxygen ratio, which is basically all you need to know is that if you're high up in the blue region, there you have more carbon products. So you look like you formed really far out, past Jupiter, past Neptune. And then if you're down in the pink region, a comet looks like it formed much closer in. In blue here, these blue points are all of the solar system comets that we know of. And if we forget about this one weird object called R2, which you can ask me questions about, by and large, every solar system comet looks like it formed really close in. So they all are mostly driven by water. There's very little carbon monoxide and carbon dioxide in the solar system comets. So they look like, remember I had showed you that the water snow line is around Jupiter and that carbon monoxide snow line is around Neptune. They look like they formed close to Jupiter. The interstellar comets, if we put here Borisov in gold and then Atlas, those look entirely distinct from the solar system comets. This is maybe a little preliminary because we only have 2 of these objects. But based on these observations, which I've shown you about, remember I also told you about those observations of Borisov that showed that it was rich in carbon monoxide. It looks like from their compositions that Borisov and Atlas are totally different from the comets in the solar system because they fall in this blue region. So Borisov and Atlas look like they formed at very, very large distances from their host stars. Whereas all of the comets in the solar system that we observe look like they formed much closer in. And I think that this is basically telling you that the objects that form at large distances, basically all of them are going into this interstellar population, like through Atlas and Borisov. And in the solar system, these are the ones that are left over. So it kind of makes sense that if you form further out, you're less loosely bound to your host star, and then it's easier for you to get ejected. I think that's what that's telling us. And that's very exciting because these interstellar comets are potentially telling you about a totally new type of comet and giving you new insights into comet formation in totally different environments. Okay. I'm going to stop sharing really quick. I'm going to share in a second. I just want to jump to a little bit further in the talk and give you some exciting future prospects. And then I'll go to questions. And I want to check the chat too. Okay, awesome. So 5 more minutes and then questions, okay? So 3I Atlas is super exciting, but we have many reasons to be excited for interstellar comets because the Rubin Observatory, I think all of you know what Rubin is, but basically the Vera Rubin Observatory, LSST, just came online a few months ago. And LSST gives us, this is an image of the actual telescope. It's in the Atacama Desert, and it's going to be observing the entire southern hemisphere almost every night, but up to 5 orders of magnitude more sensitive than any all-sky survey that we currently have. So it should be finding many more interstellar objects every year, potentially something like a handful of new 3i Atlas-like objects. This is the work I'll just highlight quickly of a student, Devin Hoover, who worked with me for his senior thesis. He's now a PhD student at the University of Arizona. But he basically did these detailed simulations of what interstellar objects LSST is going to find. What this is showing you is this whole sky, and then in red is where LSST looks. And then the color is saying where you're going to find more interstellar objects. And the answer is that LSST should be finding somewhere between something like 1 to 20 interstellar objects every year, based on just the discovery of Oumuamua and Atlas. And I end on, what about the most exciting thing we could do is not only find them and characterize them remotely, what if we could send a space mission to an interstellar object? When Oumuamua was discovered, this is the first thing I did as a third-year grad student. So basically, what you're seeing here, this is a hypothetical space mission that goes and rendezvous with Oumuamua. So blue is the Earth, and red was Oumuamua. And then all I said was, okay, October 26th, that's when Oumuamua was discovered. But let's say LSST was online. So let's say when Oumuamua came through the solar system, we would have discovered it well before July. If we had had a spacecraft that could have gone, then what I showed was it would have been actually pretty straightforward to get to Oumuamua. You would have only needed to give a spacecraft a delta V, which is a change in velocity. That's kind of a metric of how much impulse you have to give or rocket fuel you have to give a spacecraft. You only need something like 4 kilometers per second to get to Oumuamua because it came really close to the Earth. So the point of this was not to say that let's go to Oumuamua. It was to say that in the future, when LSST starts finding interstellar objects, it is very feasible that some of those we might be able to go to. Here I have, this is what another thing that we did right when Atlas was discovered. This is work from Atsuhiro Yaganuma, who's a student here at Michigan State. But basically, what he showed was that right when we discovered 3i Atlas, we actually could have sent a spacecraft, one of our existing spacecraft, to 3i Atlas. So we could have, Atlas, what you're showing you here, this is in blue, Atlas's trajectory. Getting there from Earth was pretty hard, but Mars is shown, and 3i Atlas actually gets pretty close to Mars. And we have spacecraft at Mars, which still have rocket fuel left to do things. So if we had, basically what Hiro showed was if we had launched by, say, October, one of these missions like the ones at one of the spacecraft at Mars, we could have actually got to 3i Atlas. Obviously that didn't happen, but the point is that of the interstellar objects we've discovered, 2 of them we easily could have gotten to with a spacecraft. That is extremely exciting for the future, because what that means is that if we find new interstellar objects, if they look like Atlas or Oumuamua or something like them, it's very feasible we could send a spacecraft in the next 5 to 10 years. Devin also showed this. So basically, the way to read this is Devin had all of these synthetic interstellar objects, and you're reading this like, of the objects that LSST finds, what fraction of them, that's the y-axis here, is the fraction of objects that you could get to with a given change in velocity on the x-axis. So the takeaway is that black dashed line, if you say, let's say best case scenario, you're getting like 10 kilometers per second, you could go, of the ones that we're going to find with LSST, about 1 in 5 to 20 of them are feasible targets. If you find 1 to 20 every year, that means that I'm projecting, but in the next 10 years, we're potentially going to have multiple targets for a dedicated space mission to an interstellar object, where we can get an unprecedented window into our newest unprecedented window into planet formation throughout the galaxy. So I will stop talking now and take questions, but thank you very much.
First of all, Darryl, thank you for a fascinating talk. Your enthusiasm and energy is inspiring. So let's come off mute and thank Darryl.
Thank you.
And hand over to Will to marshal the question.
Great.
Terrific talk there, Darryl, as Neil mentioned.
So first of all, we will go to questions from our own members on Zoom. And so maybe we kick off with Ian Smith, if you want to go for your question, if you want to unmute and ask a question, Ian.
Hi, yeah, of course, thanks for the presentation. It was really interesting. Just a few days ago, there was a astronomy telegram which showed the spectral analysis of comet K1, and given your comments about the average composition of comets, this one was found to be mainly nitrogen monohydrates. So I wonder if you could comment on that.
Yeah, so I didn't actually see what you're talking about. Can you send that in the chat or send it to me?
Sure.
I don't want to okay, I guess I should speculate. I don't want to speculate too much without having read it. It is, I guess I will say that it is not it's not unprecedented for comets to have like different compositions than the norm, right? So comets, as people here I'm sure know, like they're kind of weird and wonderful because each one is kind of unique in its own way. It's very typical that a comet will misbehave. That's why they're kind of a headache to observe. Okay, I got the, thank you for sending, Ian. So I see. So this was NH2 species that you're showing me.
Right.
The HST spectrum. Okay. So I was going to say that if you remember, I showed you the composition of comets in the solar system and how they compare to the interstellar comets. But I said, let's forget about this guy, R2. This object, R2, is so weird that people had even like hypothesized maybe that was interstellar too, and it was a long period comet, so has an almost a hyperbolic orbit. This object also similarly had a huge amount of N2, so it had a bunch of nitrogen compared to water and a bunch of CO. So it's like certainly not unprecedented to have different compositions. What I'm seeing in the spectra you just sent, thanks for sending that object, those NH2 species, I believe are like, I'll get back to you on it and take a closer look, but I believe those are seen in comets. Like you will see those in comets. I would be surprised if there wasn't water as well. The main thing is that I didn't get into the details of this, but like what really matters is the comparison, the fraction of a species like N2 or CO to water. So if it's water with a little bit of CO or CO2, we do see that routinely. Water with a little bit of NH3 or NH2, we do see that. But if it's like all carbon monoxide or more carbon monoxide or carbon dioxide than water, that's what's really tough to explain. Does that answer?
Yeah, sure. I was just wondered how it fitted into the general rules. Thank you.
Thank you for sharing.
And we'll now go on to a question from one of our members, Jim Barron, if you want to unmute and ask your question.
Hi, Darryl. Just in terms of your slide that was showing where the interstellar comets originated, I was wondering, is that dependent on where the giant planets are in the system, given that in some of the extrasolar systems, they have hot Jupiters, so the massive planets are close into the sun. And then along those lines, I was thinking, what about binary star systems? How would they might distribute comets as well? As any thought being given to that? Thank you.
Yes. So I can send. So okay, that is a very insightful question, which you are right to ask because I totally swept that stuff under the rug. The fundamental thing, though, is we don't actually know how interstellar comets get ejected. What produces them? We know that there's a lot of them. We know that if you take the number implied in the galaxy, it's about an Earth mass of material in the galaxy per star. The most natural mechanism to eject them would be a giant planet that's kind of far out, which could eject stuff. And the reason that's the most natural mechanism is because we know that that happened in the solar system. So by the existence of the Kuiper Belt and the Oort cloud, we know that early on, the Jupiter, Uranus, Saturn, and Neptune probably moved around, scattered a bunch of material out into the Kuiper Belt and Oort cloud, and also ejected probably more, like 30 Earth masses of material into interstellar comets. We cannot, though, this was just like, I was kind of like using the giant planet thing as an example of what could eject them. But there's lots of different mechanisms to eject them that have been proposed. You mentioned circumbinary systems. That has been investigated, and actually it turns out that circumbinary systems are much better at ejecting material, especially material closer in, to the point where at first, when Oumuamua came through and wasn't obviously active, people were writing papers saying it must have come from a circumbinary because that's where you could get material that wasn't icy, but then it had a non-grav. So the story clearly changed. Very astute question. I would say my story about giant planets ejecting, the reason I told it, and I feel okay with having like swept that under the rug, is that the statement I made about that ejection is chaotic, so a similar amount of material has to get injected, that doesn't care about what is driving the ejection. So whether it is giant planets or something circumbinary, something else, like you could imagine stellar wind blows material off, like anything like that, that will still, the ejections being chaotic still applies.
Thanks.
Now, we got a question. I think it's from yourself, Mark. I can combine this with a YouTube question if you want, or do you just want to say your question, Mark? It's up to you. I will go ahead and combine a question from Mark, I think, which is all about this media hype. And I'll just combine it with one of our YouTube questions. Again, asking about the...
Mark said that's Neil, not me.
Oh, right.
Yes. So Darryl, my question's around what challenges do you face trying to do the science in the middle of the media frenzy and public media hype around interstellar objects and comets coming close to Earth and so on?
Believe it or not, I have never gotten that question. So I thank you for asking that. I mean, the biggest challenge, that's fundamentally the biggest challenge with the interstellar comets, barring the hype, is just that they come and leave. So it's very stressful immediately. Like July 1st, I was super excited, but also it was like everybody full pedal to the metal, working nonstop. And it's kind of been like that every day since, because this is our only opportunity to look at it. So we're starting in a high pressure situation, right? So we start with an amazing opportunity, but also like we got to get the observations. Like we got to figure out what's going on with this object. Like if we don't get observations of it, we'll never get another chance. It is frustrating to get, it is challenging to be answering the same questions, not from you all, but right from reporters or public people over and over again, when every observation that like the challenge, it's challenging to keep answering the same question, right? Like the reason we have these amazing observations and we're able to say things like, oh, it's CO2. Like Martin Cordner was able to get JWST time, figure out it was CO2. The reason we figured out it was hyperbolic right away. The reason we did that is because even though interstellar comets are a new population of objects or a new astrophysical phenomenon, we have been studying comets for more than decades, right? Like we all know this. Like you probably know this better than I do. Like humans have been amazed by and studying comets for hundreds of years, and we have gotten extremely good at it. So all of the reasons we are able to get any of the observations and interpret any of them so far is because this object is so obviously a comet. So it's displaying all that's got some weird properties, like a weird composition that is giving you insights into planet formation around other stars. But we are able to get these amazing observations and interpret them because we have kind of really, really finally adapted and worked on the tools to be able to make those measurements of comets for decades. So it's frustrating to be like explaining that we're good at this because it's a comet and because we have gotten very good at doing observations of comets. Does that answer? It has been.
Thank you. Yeah.
It has been a little frustrating.
And if we could just add to that, Darryl, just from Paul Lewis on 9860 on YouTube there. What do you think about some of the speculation from certain professors like Professor Avi Lieb and stuff like this? We have to talk about these things, and I just wondered, it can just be a very quick one-liner. What do you think, or if you think there's any sort of merit in some of the talk of, still things like aliens and stuff like that?
Well, I guess like I said before, we have been studying this. It's like, here, I'll share my screen one more time. Bam, here. Like this is I know, so okay, my secret is that I'm not really a comet observer. Like I do a lot of different things and I work with a lot of really brilliant observers. And so I don't spend a lot of time every day looking at images of comets, but to the people who do that and are very good at identifying activity on distant objects, this is like clear cut evidence of cometary activity. So just this tells you that this object is cometary. So it looks exactly like what distant comets, these images were taken out past 5 AU, right? So from day one, literally day one, July 1st, we knew it was active. And then we were like, oh, okay, so it's active. So what are all the exciting things we can do about it? So we're all kind of the scientists are focused on it's not a question of is it a comet or not. We're just focused on how can we best observe this object. But in every single way that we'd expect a comet to behave, despite some compositional, like minor differences in things like composition, it is behaving like a comet.
Absolutely fine. We just had to touch on it. Mike, would you like to unmute and ask your question?
Yeah, I was curious during the talk, Darryl, about the physical mechanism for the variation in deuterium-hydrogen ratio that you showed early on.
Oh,
and wondered whether that was because hydrogen was going to outgas more than deuterium.
Okay. Yeah. Excellent question. So it's that is a subtle thing. Okay, you're asking, which is very insightful. I brushed this under the rug, so it is right of you to ask. I caveated that with saying, think of deuterium to hydrogen like just some tracer of chemical compositions. That was to qualify the statement that we don't really know where the Earth got its oceans from. And one idea is potentially that comets delivered water to the Earth. And we can kind of have some identification of that from deuterium to hydrogen. And you compare the deuterium to hydrogen in water in the Earth's oceans with that you see in the interstellar medium, and that what you look at in comets. It is not quite as much. So, okay, let me try to get this right. You asked about how the outgassing could affect the detail.
Yeah, what I was really looking at was it's obviously come from the interstellar medium because that's how the solar system forms. So you've got that original D to H ratio. And then somewhere there's got to be a mechanism for changing that ratio. And I was trying to work out what that was.
Oh, right. Okay. So the reason that we think that the water from Earth could have come from further out, the D to H is a great tracer of the temperature at which the ice froze.
Right.
So you can adjust the temperature. If you form further out in the disk, you have a different D to H. That is
Okay.
something that we know. So it's actually, there are also mechanisms to change the D to H, like in the ocean. For example, like the D to H of if there was water on Mars, if you like lose material, you preferentially lose deuterium compared to hydrogen. There are complications on top of it, but if you look at like a fossilized remnant, like a comet, presumably that tells you, that D to H tells you how far out you were. So the idea is that the D to H is different from what it would be right around Earth. That's really the key thing. Of course, though, you'll probably come back and ask and be right to say there are a lot of things that can change the D to H. There's a lot of things that are kind of swept under the rug there.
That's okay. That's fine. Thanks.
And
I want to say quick, it's also very difficult to measure deuterium to hydrogen. We did it like a handful of times successfully remotely on a comet. So it is also a very difficult measurement to make.
Okay, cool.
now if we could move on to your question, Norman, if you want to unmute.
Yeah, it's really that the idea of the comets, I presume that they are more likely to be from very early in their star formation, so that they get formed and they get ejected fairly early on. And it's at that stage the planets haven't sort of done a lot of migration. You might not get them. The large gas giants will still be well out at their distant orbits where they form, rather than having moved in to become hot Jupiters and so on. So what we're seeing is sort of primordial material that's been recycled and recycled and recycled.
Yeah, and I think so. One thing that I think I'm hearing, and I agree, like if I can expand upon one of your points, like while I think you could kind of take what you're saying and flip it on its head. So there are two lines of evidence that to say that the interstellar comets were ejected very early, like are very primordial, which is what you're saying. So one thing is just if you look at Borisov, having so much CO means that it couldn't have stayed in its planetary system for very long, because if it did, the CO would have been removed. So just a step further is that like the compositions of these interstellar comets not only tell you they formed at high locations, they probably got ejected very, very early on. So I agree with that. There's another line of evidence that makes that true, which has to do with the star formation process like you're talking about. But if you look at recent evidence has basically demonstrated that if you look at very young star forming regions, you see this huge excess of free floating Jupiter mass bodies. So that's telling you that a lot of material gets ejected like extremely early. So I would then say, Norman, what you're saying, I would take it a step further and say that my interpretation of that is that the interstellar comets that we're seeing, the fact that there's a lot of them, and the fact that they have these like hypervolatile rich compositions and must have been ejected early, tells you that whatever dynamical processes led to the migration of planets, which you're hinting at with the hot Jupiters and stuff, I think that the interstellar comets are telling you that happens extremely early as well. Like all of that gets finished by the time you're really like ejecting that stuff, or by the time you're done ejecting it, those kind of early dynamical evolutions have occurred. I think that is what I'm really glad you asked that question, because that is what I think is the most interesting takeaway from the interstellar comets.
Yeah, and presumably as well that they are or have been part of that process of moving large planets in further into the on their orbits.
Yes, that is also true.
Taking energy out of their star systems.
In fact, yeah, that's exactly right. So I think you probably already know this, but for other people who are not familiar, while people argue extensively about the exact details of early solar system formation. One thing that we do agree on is that the giant planets probably moved around and ejected a bunch of material. That was very possibly caused by interactions with comets and asteroids, exactly like Norman's saying. So not only, it's like the interactions that end up ejecting comets, that also is very feasibly what triggers early dynamical movement of giant planets, early evolution of planets. And I am pretty sure that the interstellar comets are telling you that all that interesting action probably gets triggered similarly, but it happens kind of ubiquitously throughout the galaxy at early times. And that is, like, as far as I know, like, this is our only window into that. So the interstellar comets, if that's what they're telling us, I think that is like a really remarkable takeaway about planet formation.
Thank you. And just moving on to Ian, did you have a question there? Or if you want to, you can ask your question.
Yes. How much time is left for the various observatories to make useful observations before it's too far away?
We have tons of time, actually. So it depends exactly on which observatory you're talking about, but like well into spring, if not summer. So we have many, many months left to observe this object. And so I am kind of just as excited about the data that we're going to be taking in the next several months as what we've already gotten, if not more excited.
How about humble amateur telescopes?
What was the question? Sorry, you broke up.
How about humble telescopes, amateur telescopes?
So amateur telescopes, you should certainly be observing. I mean, it depends on the exact telescope. So I could lead you to some resources to figure out exactly for your own setup. But the next like month is the perfect time to observe it. So in a couple weeks, it's going to be the most observable from Earth in December, like through kind of up till like mid-December-ish. So I highly encourage you all to get some observations from Earth. I am also going to be trying to observe it even with like we have like a observatory here at Michigan State, which is not kind of like, it counts as basic. It probably wouldn't count as like in the same class as like Atlas or one of these fancy telescopes, but I'm still going to try and get it in December. So I encourage you to try to get it yourselves if you have the capability to. And then my request is that please let me know if you get any data and send it to me, because I'm very interested to see whatever you get.
Okay, will do.
Excellent. And Glow, you've got some question there and comments. Would you like to unmute and have a chat and ask what you want?
Yeah. Thank you for really wonderful talk and keeping it simple enough that I can understand. I just wanted to ask, like, just really generally interested in water because I study water. Is it like really showing up as an abundant material or element in the universe? And assuming that what you're saying about the ubiquitous sort of like, the primordial plasma or whatever you call it, that star system formation and things like that come from. Is it really that ubiquitous, or is there other, there are, like Ian has pointed out, there are other elements in other comets or interstellar objects?
Sure.
So does that tell us about the composition of the universe, shall we say, in a grander scale? But also, could we use information from these interstellar objects, or whether is it maybe really hard to do, but like how to trace their trajectories or where they come from, and tell us about distribution of elements around, different solar systems and so on, and what else could they tell us? What else could these interstellar objects tell us that we haven't explored, do you think?
Okay. Thank you for asking that, Glow. So, okay, I heard several different questions, but there were very insightful questions that I like. Each different aspect I'm trying to wrap my head around, but I know that I have some answers for some very insightful questions you asked. So if I'll try to start for sure, I'm glad you also are interested in like the elemental makeup of the universe and compositions. I do think for sure these interstellar objects and interstellar comets in particular tell us about maybe not the composition of the universe overall, but the composition at least of different planetary systems. So what the distribution of kind of compositions of things that you see. Water, I said water was ubiquitous. You do see, I guess I can dial that back a little bit. You do see water as the primary driver of activity in most comets. But Borisov and Atlas, while there is water present, there is other things like carbon dioxide and carbon monoxide in more abundance, at least our first observations were showing that. So, and then the final thing that you said was really insightful about, can you take their trajectory and tie something between the compositions and their trajectories? And I'll just throw the word kinematics out there because basically the trajectory I kind of think of as the galactic kinematics, which just means how it's moving. The sad short answer is no, because you cannot trace a trajectory of a given interstellar object to any home system. The reason for that is that the galaxy is chaotic. So you don't actually know, and you don't know the positions of stars, positions and velocities of stars well enough to backtrace. However, the how fast an interstellar object is moving when it enters the solar system is related to how old it is, because older things in the galaxy tend to move a lot faster. We know that from stars. And the reason for that is that the longer on average something is orbiting in the galaxy, the more times it has to kind of gravitationally scatter off of something like a giant molecular cloud, some substructure in the galaxy. So the cumulative effect of all of those scatterings is to make older things move faster. So while you can't take an interstellar object and trace it back to a home system, you can say roughly how old are these different interstellar objects based on their trajectories, and then tie that to what rough age of a stellar system, because we know different types of stars are older on average or younger. Like blue stars, the biggest stars are much younger than red stars because they kind of go through all of those blue massive stars burn up all their fuel really quick, so none of them are left. So if they form, their lifetimes are only things like 10 to the 7 years, say. So for sure, I think something that's really interesting that we can do, especially kind of moving forwards once we find more of them, is to look at an interstellar comet and look at a bunch of them and see what the distributions of their compositions are and their kind of kinematic ages, which is kind of what you were saying with their trajectories, like, and then say, do we see kind of statistical trends where, I'm going to make one up, right? But like maybe the older stuff seems to be more enriched with carbon monoxide, but the younger stuff seems to be more enriched in water. I just made that up, but those are the types of things that I think could tell you a lot about combining all of those informations, just like you aptly suggested, is the way forward for figuring out what they're telling us about planet formation.
Thank you. That's really interesting.
Thank you.
And I actually have a comment from Mark. My apologies to our amazing president, Neil, for confusion earlier. But Mark just says, and I'm saying this out loud so our YouTube viewers can hear, that we have it scheduled to photograph and image Freya Atlas in our remote telescope Azero in Spain for tonight.
Oh, awesome!
So
posted.
And you've probably heard about Azero, which is, we've got fantastic setup in our remote section of an observatory there, which we can control. So hopefully there'll be some more images coming, as well as from everybody else.
That's very exciting. Thanks for sharing that.
So that's great. Are there any further questions from our members on Zoom?
No, I think we're good, Will.
Excellent. I'll just add one question from YouTube. It's been very good response from our YouTube viewers. And you've talked about the composition and stuff. What's your own sort of gut feeling? I know we can't tell, but do you feel that Free Eye Atlas is purely organic, or could host some amazing stuff? What's your sort of feeling about it? And I'm personally just wondering, is there any way you could do spectroscopy or something like that to get any gleams about its composition?
Yeah, so people have, so the JWST observations I showed, which are not mine, those are due to Martin Cordner, Dennis Bodowitz, and this very, very excellent team of people. Those were spectroscopic observations. So we have gotten some, and those have revealed the presence of CO2. We've seen water. I have been part of some observations that we've gotten of things like CN. The weirdest ones, like organics, not yet, but you kind of like, the more spectroscopic observations that we get, the better information we'll get. We did have a very strange, not even strange, like we've seen it in comments before, but there was the spectroscopic observation from the VLT led by a group of astronomers down in Chile. Thomas Puzia was the person who obtained the observations, but they saw this weirdly high nickel spectroscopic feature. So that is pretty interesting as well. So I don't want to speculate because I kind of know that comets they're continuously changing. That's why they're awesome, but also kind of difficult, because effectively what is going on is you have a nucleus that, say it's a kilometer in size. As it moves through its trajectory, you're taking stuff off of the top, outgassing. You are literally seeing further into the nucleus. So of course it changes. So like, the activity that was being driven out, I showed the TESS images. What was driving that is certainly different than whatever is going to be driving things in the next couple of weeks. So I don't want to guess, but I'm excited to see what other species that we detect coming off of it.
Fantastic, exciting stuff. That's really all the questions there, Neil. So over to President for.
Great stuff. Thank you, Will. Darryl, can't thank you enough. Your enthusiasm and passion for the subject is tangible. And we really appreciate your encouragement. As a astronomy society, we're keen on observing and imaging, but we're also keen on the science and making a contribution. And you've heard about our plans to capture images from ASIRO, and thank you for highlighting Andrew's contribution.
Yeah, and thank you all for coming and excellent questions, and definitely keep me in the loop with whatever observations you get.
Can we all thank Darryl again for his fantastic presentation this evening?
Thank you. I'm blushing, or maybe I'm just red in the face because I was talking for an hour, but either way, thank you all. It was really fun to be with you. Thanks for the opportunity.
That's brilliant. Thank you for joining us. You're welcome to stay on and hear about what we've got coming up.
Okay, I have to feed my cats, so I really need to go home, but thank you.
Thank you again, Darryl.
It's a pleasure.
Okay, to close out the evening, let's have a look at what we have coming up in the next few months. We have one event remaining in November. Next Friday, our public outreach event at the House of the Bins, West Lothian. Most of the arrangements for this are in place now, and we're fine-tuning things like targets and materials. There's only one major thing left to arrange. I'm sure you don't need me to spell out what that is, because I might jinx it. I will do what I can with my presidential powers, but I will need you all to be rooting for us. Then we head into December. On Friday the 5th, our main AUC hybrid meeting, we have Dame Jocelyn Bell Burnell, who will describe some of the more amazing or surprising things that we're finding as a result of improvements in telescopes and detectors. And with these improvements, astronomers no longer have to use long exposures or long integration times. We are now seeing short duration events and variability on short timescales in many branches of astronomy. And the talk this evening is another example of that, where we're looking at an object over the next few weeks. On Friday the 19th of December, our mid-month online meeting, Dr. Tim Pearce will give a broad overview of Kuiper belts around other stars. We've talked a lot about solar system formation and planetary disks. In this evening's talk, there's more of this next month. We know that our solar system contains not only planets, but also the smaller bodies that we've covered this evening. And these bodies are sometimes collectively called debris, and they tend to be concentrated in disks like the asteroid belt and the Kuiper belt. We can image belts like the Kuiper belt around other systems, and these belts show a range of shapes and features. So it promises to be a fascinating talk, a good follow-up to this evening's talk. So join us on the 19th to hear more about debris. And if we finish 2025 with a bang, things are staying just as hectic as we start 2026. Our first meeting is on Friday the 9th of January. Note, that's obviously not the first Friday in the month. And in a talk entitled Growing Up in a Rowdy Household, Moira Jardine, Professor of Astronomy at the University of St Andrews, will look at the impact of stars on their planets, especially early in their lives when the star is most active. Moira says that a star and their planets are not independent, they evolve together, and each can influence the evolution of the other. And studying other younger versions of our sun can help us to understand these processes and to see the evolution of our own solar system in the context of other stars. And then on Friday the 23rd of January, our mid-month online meeting, I'm delighted that Nigel has been able to reschedule Professor Claudia Durham's talk, which was originally intended to be held in September. And Professor Durham from Imperial College London will share the secrets of gravity. Gravity is the overarching miracle connecting everything we know and the reason the universe itself can even exist and evolve. So join this journey as we push the limits of knowledge and navigate through the foundations of space-time, underpinning the origin and the fate of the universe and that of everything in it. And if that doesn't get you going in a cold January, then nothing will. And then finally, in the middle of the month, on the 14th, we have our imaging and observing group on Wednesday, the 14th of January. So that brings us to the end of this evening's agenda. I look forward to seeing some of you next week and everyone else the week after that. And with that, I wish you all a good night and, of course, clear skies. Thank you all.